This presentation will be on torque from Module 9 and include simple machine examples and discussion on mechanical advantage. Torque is very simple. It's just the force applied to a lever arm, which can be thought of as a bar, that's perpendicular to that bar. So think of the force you apply while pulling on a wrench. It's perpendicular to the handle of the wrench, and you cause a rotational motion. And the formula is simply torque equals force times radius. And the radius is the length of the lever arm. And torque works through mechanical advantage, which is just the amplification of force by use of a tool. Very simply, levers work based on this principle of mechanical advantage, and the equation is it's the length of the input arm divided by the length of the output arm. So what that means is the closer your fulcrum or the pivot point is to the mass you are trying to lift, the greater mechanical advantage you will have. If I have an input arm that's 3 meters and an output arm that is 1 meter, I have a 3 times mechanical advantage. If they're the same, I have 1 mechanical advantage. I don't have any mechanical advantage. Of course, mechanical advantage and levers have been used extensively throughout history, from building the pyramids and catapults and machines that were used in wells to gather water. And today we still use them too, like with car jacks and torque wrenches. So practice problem is from Module 9, Item 2, and this is a torque problem, and it asks the torque that supports A and B exert on a diving board when a 56 kilogram diver stands on the end of it. So for part A, it's very easy. It's just T equals force times R. Force being mass times acceleration. We have 56 kilograms times the force of gravity, which is what is exerted on the diver. And our mechanical advantage, our R, is 3, because we choose to use B as a fulcrum between A and the diver. The diver would be our input arm, and the distance between A and B is our output arm. For part B, it's the same. We're going to use the 1,646 Newton meters of torque that we found in part A, because the diver is still exerting that much force on the board. But now we also have to calculate the torque that A exerts on B. B, it's still our fulcrum. It has forces from both sides. And that's very simple. Our R is 1. There's only distance 1 meter times 56 times 9.8. Same kind of forces here. And if we add those two together, we get almost 2,200 Newton meters of torque. Part C asks the same. It says, what is the torque that A exerts on the board if the board has a mass of 46 kilograms? Well, we can treat the board as a single particle through summation of moments. And basically what that means is we can say the board is a 46 kilogram particle at the center of its equilibrium. So it will be 46 kilograms at equal distance between the ends of the board. And so that being said, the force of A is still 1,646 newtons, but we are going to add the force of the board. So we're going to take 46 kilograms times 9.8, and R isn't 0, it just isn't counted. And we can add these two numbers together, and we get a torque of a little over 2,000 Newton meters. Part D asks the same of B. It says, what is the torque of B, given the board has a mass of 46 kilograms? And this one's a little bit more tricky, because B is still our fulcrum through the whole series of these questions, but we are going to have to double up on our value for the board. If we look at B, we know there's a piece of the board to the right and left of it. So even though we treat it as a particle, the board exerts a force to the right of B on the input arm and to the left of B on the output arm. So we double up because there's twice as much force given this point of reference of B. So we still have the force of the diver, the 1,646, plus 2 times 46 times 9.8. That's the force of the particle, the board particle we're treating as. and then we add A, 56 times 9.8, force of A. We add those together, we get a little bit over 3,000 Newton meters of torque.